So today we'll pick up where we left off, kind of introducing the idea of probability. So one thing that I had said last week, I kind of changed my mind on after my other section, getting back to my office is, so I talked about the next Learn Smart, and I think I said maybe it was gonna be due before class Wednesday. So I just put that up there this morning before class, and I really just like cut it in half. So it's a really short, I have a targeted time on it. The targeted time was like 5 or 6 minutes. So, just by the time we start class on Friday, so you've got the next kind of 4 days to get that done. I would suggest you getting it out of the way today or tomorrow real early, and then kind of having the rest of the week to focus on that Connect and Excel assignment, which are due at the end of the day on Friday. So that Learn Smart is due before class. That first Connect and first Excel, which have already been kind of assigned last week, that's due at the end of the day Friday. So I've already had some people ask me questions on that via email. I've got a couple of Zoom meetings set up, so start working on that. If you have questions, feel free to reach out and we kind of try to schedule something to get those questions answered, okay? Any other questions for me before we kind of dive into the material today? Everybody's okay with things? Anybody on Zoom? Let's see if we got. All right. So let's get going here. Oops. Here we go. So we left off last class kind of looking at these contingency tables. Right? I said by the end of this week, we'll build our own, but for now, just kind of we're given this contingency table. We know the probability of certain events, maybe the probability of their complements. And we said the way that we read this contingency table is if we want to find the probability of A, right, we'll go over that total, right, and that 0.6 is the probability of A. We also kind of briefly touched on why to reproduce that total, we can either add across the rows, right, if we're looking for the probability of A or the probability of A complement, or we can add down the columns if we want to find the probability of B, which is 0.5, and the probability of B complement, which is 0.5. We could just add kind of down these columns to reproduce those answers. Okay? And I'll review some of this once we get to Excel on Wednesday and we build our own contingency table. So the other thing we said was these top 4 left cells all represent intersections. So if I want the probability of A intersection with B, or the way that we typically kind of read this, A and B, right? The probability of seeing something that's in event A and event B would be that 0.4. And if we wanted the probability of seeing something in B complement and A complement, that would be 0.3. So this is all stuff we went over at the end of class on Friday, kind of how we look at these contingency tables, those totals representing the probability of the row or column that they're in, and then these top 4 left cells representing the intersection of whatever row and column heading kind of produces them. Okay? So one thing we did talk about, but I didn't show you in a contingency table, is what the union of 2 events are. So the way that we read this union, right, this looks like a U, this set symbol, is what's the probability we see something in event A or in B. So this means that it could be an experimental outcome that's in event A, it could be in B, or it could be in both. Right? So I'll show you a kind of not cheating way, but just a less kind of technically correct way of how we find this union, and then we'll talk through a little bit, and I'll kind of come back to this and show you another way we could find it. So the non-technical way is if you're looking for the union of 2 events and you have a contingency table, you can think about find the intersection of those 2 events. So instead of finding the union, find the intersection of A and B, which would be that 0.4, and just make an L. And if you add those up, that'll give you the union. So 0.4 plus 0.2 plus 0.1 be what? 0.7, and that would be our union, right? If I wanted the probability of A complement or B complement, I go to the intersection of the 2, so 0.3. I make an L, right? And then add those up. So 0.2 plus 0.3 plus 0.1. There, the union of A and B complement would be kind of adding these 3 up, 0.6, right? That's not a technically correct way of doing it, and we'll talk through a little bit, and then we'll come back and I'll show you the reason why that works is because there's a probability law that kind of floats around in the background, which allows for us to kind of use this non-technical way. Right? Okay, so let's go over a little bit here, and then we'll kind of eventually return to that. So one of the laws that we have in probability is that it doesn't matter if I'm saying the probability of A or B, that's the same as the probability of B or A, right? If I say, what's the probability somebody has, I don't know, brown eyes and is over 6 feet tall, that's the same as what's the probability someone's over 6 feet tall and has brown eyes, right? It doesn't matter, excuse me, the order in which I say that, right? So order doesn't really matter when we're talking about the union. It also doesn't matter when we talk about the intersection. I think the example I just gave was actually an and intersection, but it doesn't matter. Union or intersection, doesn't matter which way we kind of say this. If we put B, the event B first or event A first, it's the exact same thing. Okay? So it'll help us kind of down the road, but just kind of mentioning that, getting that out of the way. It's not too tough, I don't think. We can think about the intersection of two events. We talked about last class was where those two circles kind of overlap, right? If this entire rectangle represents every possible experimental outcome, we said the area of that rectangle was what? So if we think about the probabilities of events, if I add up the probability of every possible outcome I could see, we said those should add up to what? 1. Yeah, right? Same kind of idea when we're working with relative frequencies, right? As long as we've covered every possible response we could see for a variable, those probabilities should all add up to 1, the probability of 1. Or think about it as 100%, right? If we say this in kind of the normal way that we speak. But probabilities, right, are percentages kind of in decimal form. So if this entire experimental outcome space is 1, and then all the outcomes that are in event B are represented by this circle, all the outcomes in event A represented by this circle, the outcomes where those two circles overlap are going to be all the outcomes that are in both A and in event B. Okay? Right? Everything here is in both of those circles. It's in A and in B. We can think about, what about if I looked at this like half moon over here? Well, these are all the outcomes that are in A, but they're not in B, right? Here, let me, I think I have my email pulled up, so let me just, I don't want to mute that. Let me just exit the email. Where is it? There we go, so we don't get those dings throughout the lecture. So I can think about event A as being kind of two components, right? The intersection with A and B, and then the intersection of A and B complement, right? Everything that's not in B, but is in A. Okay? So kind of we think about these intersections. I always thought this was like a great meme. Like when you say it's fine, when it's actually fine, right? There's a very small overlap, right? A very small intersection between those two things. Okay? We talked about this rule last class. We're going to combine some things. So I feel like I'm probably jumping around a little bit, but we're going to take all these to understand another probability law. So the first one, which I believe I went through last class, is this idea that, well, look, if I look at the probability of A and I take the probability of its complement, so A complement is this kind of blue area, if I add those two together, that fills up the entire experimental outcome space here. So if I add the probability of A and the probability of A complement, those should always add to, we said the entire space is 1. For instance, think about it this way. If I tell you the probability that someone has blue eyes is, I don't know, 0.1, the probability that they don't have blue eyes is 0.9, right? The remaining, right? If I don't have, if you're talking about it, do I have blue eyes or do I not? Those are the only two possible outcomes. Those two have to add up to 1, right? So if we rearrange this a little bit, you can kind of see it's the probability of A plus the probability of its complement equals 1. We rearrange that so that if I ever know the probability of A, the way I can get the probability of its complement is just subtracting it from 1. I said the probability someone has blue eyes is 0.1, then the probability they don't have blue eyes, the complement would just be 1 minus 0.1 or 0.9. Okay, that's kind of what I'm doing there. Okay, so I remember kind of going over this last week. So now we're going to take some of these things that we know and build something a little more complicated, which is if we want to find the union of two events, right, I can break these down into kind of different components, right? So first is, I think, the easiest way to think about this. If I take the area of circle A, so the probability of A represented by this circle, and then I added that to the probability I'm in B, or circle B, what I've done is I've double counted what's in both of them, right? So if I take this circle A, I add to it this circle B, I've double counted this region, right? So how can I not double count it? Well, I just subtract it one time, right? And that way I've only counted it once. So if you ever want the union of two events, am I either in circle A or in B, or am I in both? I can just take the probability of A plus the probability of B and subtract out what I double counted, which is that intersection. Okay? Now I'll show you a slightly more complicated way of thinking about this, but this is the easiest form in which we can find the union. Okay? So is everybody okay with this? Does this make sense? Any questions on this? Make sure there's nothing in the chat. Okay, so I think, yeah, the easiest way to think about it is, clearly I can see I would have double counted what's in between. So if I subtract it out once, that'll give me the probability that I want. Let's go. I'm going to break that union down into 3 different components and show you a slightly different way of thinking about it, which will hopefully relate to once we see it in the contingency table and what we're doing there. That kind of little make an L, hopefully it'll make a little more sense. So I've got this entire experimental outcome space, and I've got circle A and circle B here. I'll do my best to show this to you. So if I first, probably the easiest one, right, to think about is what's in both of these circles. We said that represents, right, the intersection of those two events. Okay? If I then think about where would B complement be? If we went back to that slide where I showed you just A and A complement, if this is circle B, B complement is everything that's not in circle B. And this is where occasionally having multiple colors, kind of taking notes in this class might help. I'll try to do it so that even if we had the same color, it would make sense if you're reproducing this. So we can think about this blue area as B complement. So if I think about, all right, what is both in circle A, right, and not in B, right, or in B complement? Well, it would be the blue area. Here, I'll draw it like this. It'd be the blue area that overlaps with this circle A, right? That kind of half moon right here. So really what I just found was everything that's in circle A, but not in circle B, right? Outside of that circle B. So if I'm in A and not in B is just B complement. I'm putting the wrong color caps on different markers. I'm gonna have a mess here. So if I then want to think about where would A complement be? Well, A complement would be everything that's, and I'll try to draw these horizontal, everything not in A, right? So these kind of horizontal lines would be A complement. So this half moon over here is everything that's not in circle A, but is within circle B, right? So this area here, I could think about is the probability that I'm in circle B, but outside of or not in A, which if I'm not in A, that's A complement. So I can actually break this down, the union of A and B, I now have it broken down into 3 components. This kind of half moon, this half moon, and then what's in both of them. So if I simply add them up, I'll then have the entire area of A union B. Right? So if I add these 3 components up, I'll end up with the union of those 2 events. Now, like I said, I think this is a little bit more complicated way of thinking about the union. It's probably easier to just think about, I'll take the probability of A plus the probability of B and subtract out what I double counted, which was the intersection. But you could actually think about it this way as well, okay? And I'll return, oh, this wasn't on the screen there, sorry. So we'll think about the contingency table and how we would find these 3 components. So I'll show you a couple different ways you can find that union once we go to a contingency table that doesn't just rely on this like making an L, I said kind of technically not correct. Okay? Any questions on this before we keep moving? Any clarification? We're okay with this? Okay. Let's go back here. See if we can get this to switch over relatively quickly. Yeah. Oops. think I want to come back here. So we'll go to the contingency table first. Okay. So let's say I want to find the union of A and B. Before I said, well, how could we do this? Well, we could take the intersection and make an L, right? So before I think I have some different stuff on this slide. So if we go back to the original slide I showed you, where is it? Nope, nope, nope. There it is, right? The technically not correct way. Well, what was this really doing? It was taking the probability of A and B, which is kind of that, what was in between, or what was in both of them. It was then taking the probability of B and A complement, which was one of those kind of half, like crescent moons, and then the probability of A and B complement, which was our other kind of half crescent moon. So really the reason why this works is because these were the three components that I would have needed if I'd broken that union down into those two crescent moons and then kind of what was in the middle or what was in both of them, right? So that's why this works. What I think is easier is taking this rule where you know the union is just the probability of the two events minus what you've double counted or subtracting the intersection, which if you want to do that with a contingency table, same numbers here, right? I can find the probability of A, which is 0.6, the probability of B, which is 0.5, and then subtract out the intersection. So the intersection would be A and B, which is 0.4. So 0.6 plus 0.5 minus that 0.4, I would have gotten 0.7, which sure enough, if I made that little L here, 0.4 plus 0.2 plus 0.1, that was 0.7 as well. So either way would get us to the same answer. I personally think this is probably the easiest way to do it. Okay. Any questions on this? We're okay with this? All right. Actually, let me see. What's up here? Oh, it's me. Okay. Might try to play around with getting this. Actually, let's see. Let's see if we can try something here. I don't know if it's going to work because I think it's going to switch over in class, which I don't want to do. So let's try this and see if it works. Waiting, we're waiting. There we go. All right. So try this so you can kind of see what I'm talking about a little bit better. So remember, when we were talking about breaking that down to three components, we had these three components, right? So that was the probability of A and B complement, which would have been right here. The probability of A and B, which would have been right here. And the probability of B and A complement, which would have been right here. Right? So that was the other way we could find the union. I was referencing it in the way I was talking, but I wasn't sure if I could get this video to be up there at the same time. Okay? Okay with this? Any questions on any? All right, so we'll go back so you guys can see me if you want to. I don't know why you would. So go back down here. All right. So we talked about this. Where were we at? We left off right here. Okay. So now that we know this idea of that we can find the union by taking the probability of two events and subtracting out that middle, what we double counted, that intersection, what happens if two events are mutually exclusive? So the idea of being mutually exclusive is that I can't be in both events, can't be in A and in B at the same time, right? So this would be like when we define things as, what's the probability I make between $0 and $50,000 and that I make between, I don't know, 200 and 250,000. Well, I can't be in both those categories at once. So the probability I'm in A and B is actually 0. There's no income value that's between 0 and 50,000 and between 200 and 250,000, right? That's just impossible, right? At least in the way that we think about numbers, right? So if two events are mutually exclusive, what we're really saying is the intersection is 0, right? Which makes finding the union really easy. Because now, if the intersection is 0, we haven't double counted anything, right? There is no intersection. There's nothing that's in both of these events. So if they're mutually exclusive, to find the union of two events, we can simply add the probability of the two events together. There's nothing to subtract. You can kind of think about in a contingency table, that would look like this. You'd have to see a 0. If two events are mutually exclusive, the probability of the intersection, which is what these top 4 cells represent, the probability of that intersection is 0. So the contingency table makes it pretty easy to identify whether or not two events are mutually exclusive. Kind of the visual, if we had a Venn diagram, right, pretty easy, A and B, there's just no overlap, right? These two circles don't have any overlap at all, okay? Okay with this? Shouldn't be too wild. Once we have this definition down, I think if the intersection is equal to 0, that means they're mutually exclusive. This stuff kind of makes sense. Right? So I don't know, the example I always like this to mean like phone and internet access were mutually exclusive in the 90s, right? So I don't know, you guys are probably too young at this point, but you used to have like 2 phone lines, and if you didn't, you got a busy signal, and your parents would yell at you because people were trying to call, and you were on the internet, and so. This is the idea. You couldn't have both of them occurring at the same time on one phone line, okay? So with that in mind, we'll push this idea of the union, even if two things weren't mutually exclusive, we'll push it a little bit further, right? And this is probably about as far as we'll push this, and then we'll kind of switch over to thinking about conditional probabilities. So, if I look at this Venn diagram here, and I remember, and this is why I brought it up earlier a couple of times because I want to hammer this, the entire experimental outcome space here, this entire rectangle, has an area of 1, right? It's every possible experimental outcome, right? So if I take what's in both of these circles here, A and B, so this white shaded area, I know from what we had just talked about, that represents the union of A and B. Everything that's in either circle A or in B, or it could even be in both. Now, I'll tell you what's outside that circle, and I'll try to give you a drawing here in a second to kind of reassure you, but everything not in that union is in the intersection of the complements of those events, okay? So everything that's not in the union of A and B is in the intersection of those events' complements, right? The A complement and B complement. So I know those two areas, just by looking at the visual, the blue plus the white area has to be equal to 1, right? It fills up the entire experimental outcome space. Well, from there, we can decompose it a little bit further because I know I can rewrite this union as the probability of A and B minus their intersection, or minus what I was double counting. So all I did was plug in what we know about how we can find that union into this equation, and I now know that the probability of A plus the probability of B minus its intersection plus the intersection of the complements have to add up to 1. Okay? And this allows us to do some things with a contingency table. It allows us to solve certain problems where we're missing one of these components, right? This is helpful because now, as long as I know 3 of these, and I know these 4 things add up to 1, I have one equation, one unknown, I can solve for what that missing piece is. Okay? So we'll work through a problem like this, but this is the general idea. Okay? So the reason why it's the intersection of the complements, just to kind of give you a little bit of an idea why, I'm not going to ask you to prove this to me necessarily, but I think it's helpful to kind of understand why that blue shaded area was the intersection of the complements. So if we've got something that looks like this, and we've got circle A, and we've got circle B, right? Where would B complement be? Well, B complement is everything that's not in B. So it's going to be this kind of blue area here. And then where would A complement be? Well, that's everything that's not in circle A. So if I kind of think about, I could draw like kind of this red shaded area over here. And then wherever that blue and red shaded area intersect, that represents everything outside of either one of those circles, which, remember, what did this red and blue shaded area represent? Well, that was A complement, I guess if I'm going to color code this, and B complement. And where they overlapped would be the intersection of those two. So that's why everything outside of our union we thought about as the probability of the intersection of those two complements. Okay? Like I said, I'm not going to ask you to reproduce that or kind of give me this lengthy discussion why. But as long as we know that that's what that area represents, then we should be okay for what we're going to be doing moving forward. Okay? Any questions on this? All right, so let's go back here. I think this might not cooperate with me on this one. We'll see if I get it right the first time. Nope. think I hit the button a little too early. There we go. So let's try to take this rule and apply it. So let's say I gave you something like this, right? I know the probability that event A occurs, so this entire circle, the probability of A is 0.5. The probability that I'm in A and I'm in B, or the intersection of those two, is 0.1. And then the probability that I'm in neither A or B, right? I'm not in A and I'm not in B. That would be this kind of light blue area, and I'm telling you that's 0.3. Okay? So if I have 3 of those components, it's really just a matter of once I have that formula, being able to plug in what I know. So if I go back here, which of these did I know? Well, I was given the probability of A, I was given the intersection of the 2 events, and I was given the intersection of the complements. So I could plug in 0.5 for the probability of A, 0.1 for the probability of the intersection, and then 0.3 for the intersection of the complements. Then the only thing I have left to solve for is this probability of B. Okay. So with this in mind, I've got my equation. I just start plugging things in. Probability of A is 0.5. The complements intersection is 0.3. And the intersection of the 2 events is 0.1. Okay. Once I plug all those values in, it's just a little bit of math. So here I kind of skipped a step. But once I plug those values in, right, I need to move everything over so that I have the probability of B as a function of everything else, which is now just numbers, right? There's just a little bit of algebra once I've plugged everything in, okay? So I plug those values in, rearrange so that I'm solving for the one thing I don't know, and I can find that missing probability of B, okay? Any questions here before we keep moving? Now, one thing to be careful on here, I guess the easy place to make a mistake. Remember, we're subtracting what we double counted. So when you plug in 0.1, you're actually subtracting 0.1. So that way, when it gets moved to the other side, that's why it became positive, even the other two, you know, we're subtracting from each side. So just remember to kind of keep that negative sign there. Okay? If you don't, you'll probably just end up with the right answer, but instead of positive, it would be negative, which doesn't make sense, right? We're looking for a probability. It has to be between 0 and 1. So even if you make that mistake, you'll probably be able to identify. I got to go back. I did some algebra wrong because this probability has to be between 0 and 1. Right? Oops, I guess I didn't have the answer up there before, right? So if we actually do this math, we'll get the probability of B here as 0.3. Okay. Any questions here before we keep moving? Where are we at in time? Oh, we're good. Okay. All right with that? You know, we could do a different one where we're missing a different component. So this time, I give you the probability of A and B. I don't tell you what the intersection is, but I do give you the intersection of the complements, right? So here it's just having a different, different components than we did before. So we can still use that same equation, but now we know the probability of A and B, so we plug those in. We then add in the intersection of the complements, that 0.5. And then we're going to solve for what we're missing. Right? Now, in solving for what we're missing, right, we can rearrange that equation. Right? All I did was, before I plugged the numbers in, actually, on the previous one, I said plug the numbers in, then rearrange. You can do that in either order, right? So here I rearranged the equation to solve for this unknown, which was the intersection of the 2 events. Once I rearrange that, just plug my values in. So the probability of A and the probability of B were both 0.3 here. The intersection of the complements is 0.5. And then when I was rearranging things, I had to subtract that 1 to move it over. So I've got that -1 sitting there. Right? Really going from here to here is algebra. If you're having issues with that, kind of reach out to me. Probably not going to take class time to like dive too deep into kind of working through every line of the algebra. Hopefully you guys have kind of handle on that at this point. But if not, feel free to reach out and I can kind of go more in depth into how we kind of go from here to here. Okay? And from that point, it's just a matter of plugging our values in. Okay? Any questions here before we keep moving? Yeah.
So the union is included or is it not included in the probability of B?
Yeah, so the union, right? If we think about the probability of B, the way that this is displayed, let me see, I could have actually had this like here, right? It's the entire circle of B. So essentially, the whole reason this equation works is because what we're doing is the probability of A and B both include the intersection, right? So that was kind of the role of like subtracting it out because we were double counting it. So yeah, when you're looking at these Venn diagrams, if you're given the probability of an event, that represents the entire circle, including if there is an intersection, including the intersection, right? It's easy. So I have a lot of people who want to try to do this in their head and not use the equations. And the issue is the visual, there's like a disconnect between the math and the visual. Because the visual here, I think what you're asking is you're thinking of, is this like crescent moon 0.3, right? But no, remember that crescent moon, just this area, that represented what was in circle B and not in A, right? So that actually doesn't represent, that represents something different. So yeah, these probabilities represent the entire circles here, which includes that intersection. That's a good question, yeah. Like I said, I know I get some people that are really stubborn. They just want to do this in their head. And then well, why isn't this right? Well, it's because the visual is not quite the way we should be thinking about it mathematically. Any other questions on that? That's a good question. Okay. All right, so there's no questions on that. We're going to dive in to kind of the next topic of probabilities, which sets us up for talking about something called Bayes' theorem. So I don't even know. I think we'll get there on Wednesday. We'll probably spend a lot of time in Excel on Wednesday, so I'm not sure how quickly we'll move through that. But this next topic sets us up. So I briefly mentioned on Friday, we have these things that are called conditional probabilities, okay? So there is a way we can find the intersection of two events, even if we don't have three of these other components. So the way that we can find the intersection of two events, or the probability of the intersection, is taking the conditional probability, and when we say conditional, remember this, the way we read this is the probability of B given, this vertical line, given that event A has already occurred. Okay? So then once we have that conditional probability, if we multiply it by the probability of whatever we're conditioning on, this would give us the intersection of the two events. So I'm going to try to show you a few visuals and then give you some examples, I think, that make this makes sense, right? So the one that I try to say is, so let's say, let's try to think of a wild example, or I'll get a little political here, so hopefully no one takes offense. I'm using this as an example because it's a generality. If I asked a person at random right now, and you can look at like survey polling right now, what's the probability, if I selected one person at random, that they would vote to support the legalization of marijuana, right? So I actually looked at this because I was curious the other day. In Indiana, I think if you chose one person at random, about 60% of people favored, okay? So that's, close to 50%, a little bit higher, right? But now let's think about if I condition on something, right? So event B here might be what I'm interested in. That event B is, does someone favor the legalization of marijuana? Right? So I think that standalone, the probability of B is 0.6, right? 60%. Now let's say I tell you, well, assume or given that now you know that one person selected at random is in fact a registered Democrat, what do you think the probability now is that that person is in support of marijuana legalization? You think it would be higher or lower or the same? Probably, no one wants to. You think a Democrat would be more or less likely to want to vote for the legalization of marijuana? More, right? By all the data that we see, that's what we see. So having this additional piece of information, like knowing that person is a registered Democrat, we now think the probability that B happens, that they are in support, is probably higher, right? Conversely, if I tell you, well, now assume event A is that they're a registered Republican, what do you think happens to the probability that now they're in support of legalization of marijuana? Probably lower than 60%, right? So having this additional piece of information, knowing that A, right, assuming that given A has occurred, given that A is true, the probability of the event you're looking at is probably different, right? So this is all that conditional probability is there. The other example I always give is, you know, if I'm walking in, and now it's a bad time because you're thinking about the current climate. Let's say, you know, I'm interested in the probability that somebody slips and falls outside of the building today. Well, given that it's very, you know, on a normal day, right, in the middle of summer, the probability that I slip and fall outside is pretty low. But given that it's snowy and icy out today, now what's the probability that I slip and fall? It's a lot higher, right? These conditional probabilities, once you have this additional piece of information, change the probability of the event you're interested in. Right? This is the idea of a conditional probability. So I'll try to explain a little bit more about why this intersection can be rewritten as this. So let's go here. And try to think about this. I'll start to draw events. Up to this point, I've always drawn them as circles. It's because it's easier. I'm going to draw them as rectangles now. Nothing changes. It's just the shape to represent them is a little different. So let's say I have this entire experimental outcome space. Okay. So let's actually, I think it's a, no, I'll do squares here. So let's think about, here. I'll give you, like, let's say this space represents A, okay? So that's event A, right? What is event B, right? Let's say event B is like, let's do this. Let's say that red kind of square, rectangle, whatever, is going to be event B there. If I just think about what's the probability that B occurs? Well, if I look at the whole space, B is like pretty small, you know, pretty small area of that, right? I would say much less than a fourth, right? But now if I tell you, okay, what's the probability that B occurs given that I know A has occurred? So if you tell me for sure, without a doubt, A has occurred, I now am thinking about the possible outcomes I could see are not this entire experimental outcome space. It's only the outcomes in this little rectangle, right? Because you're telling me that A has definitely occurred. So knowing that A has occurred, what's the probability now that I see B occur? Well, B is a very large part of that smaller circle A, right? So now if I'm thinking about the probability of B, it's going to be relatively high. Pretty, you know, if I think about what fraction of square A is made up of B, a pretty large, almost, I'm guessing here, like 90–95%. Right? So knowing that we're in a certain event, it limits the possible outcomes we could see. You can almost think about it as the experimental outcome space is no longer one, it's a much smaller area. And if B has a very strong overlap with that smaller area of A, our conditional probability is going to be much, much different than what we would call the, I'm off the screen here. Not that. Much smaller than the unconditional probability. Okay? So here we can think about this as the conditional probability of B, and the unconditional probability of B, and here we have the conditional probability of B. Right? We're still looking for the probability of B, it's just that we've conditioned on something else. Okay? Any questions on that? Just kind of giving you some examples and then giving you a visual of it, of why we see these conditional probabilities could be different than the unconditional probability. All right, so now let's try to get at, and this is going to be a pretty extreme example, but it'll sell the idea, I think. So let's say I have this entire experimental outcome space, and I'll shade it in a little bit here. So let's say this lower rectangle is event A, right? And let's say it's exactly 0.5. So I can think about the probability of A, it exactly splits this entire experimental outcome space in half. So the probability of A is 0.5. Let's then say I have this lower rectangle here, right? So just this shaded red area, that's going to represent event B, okay? And let's say if I think about B in terms of the entire experimental outcome space, I tried to draw it to scale, but it should be, I tried to draw it to be a fourth, right? Where the probability that I see B is 0.25, okay? Well, if I now think about, okay, well, what's the conditional probability of B? So what's the probability of B if I condition on A occurring? Well, if I know that A has occurred, what has like the area of my possible experimental outcomes been reduced to? If I tell you A for sure has occurred, you can't see anything, any of the outcomes up here. So the new space that you can think about that exists is that area of 0.5. So what's the probability that I'm in both A and I'm in B? Well, we said we can think about that as the probability of, and I don't think I have it on the screen here, but, I didn't want to do it this way. Well, we can run with it here. So I've limited this down to the space of 0.5. How much of that space, how much of that remaining space, now that I've conditioned on A, is made up of B? Well, the area of B was 0.25, but it was 0.25 out of an entire space of 0.5, right? So it's like we'd be dividing that probability of B by, sorry, I just got to do this a little bit differently. I'm not even, also let me know if I'm not on the screen there. So what I was doing here was, this was where A and B occurred. Now, in the example I drew, they were like perfectly overlapped, right? So that area was 0.25, and then I'm dividing by whatever space was left for the event I conditioned on, right? So this 0.5 was the probability of A. So if I want to find the conditional probability of two events, it's really just take their intersection and divide it by the space of whatever event I conditioned on. Okay? So that's kind of why this equation will work, and I'll go back to the equation, but this is like a visual representation of why that works. Okay? Now I could also have thought about that equation would have held. Let's say instead of just being down here and the probability of B was 0.25, I could have thought, what if the probability of B was something like 0.3, and this actually extended a little bit higher? Well, once I know that A has occurred, it's like none of this is possible anymore. So it doesn't matter really what the probability of B is, it matters what the probability of B intersected with what I condition on the probability of A is. So that's why that numerator is the intersection of A and B and not just the probability of B. Because if we had a scenario like this, well, now when we condition on A, this part of B we know can't occur. Okay? All right, so trying to give a somewhat of a visual representation there. But once we know that's true, we can kind of run with this probability law. And I explained it in a way that I don't have on this first slide, so I'm going to skip forward and then go back a little bit. I think it's easier the way that I explain it than multiplication law that we usually want. So I'm going to go down here. So we'll wait for the screen to catch up. Here we go. So this is what I just kind of explained with that visual, right? If I want the conditional probability of two events, I'll take the intersection and then divide by whatever I'm conditioning on, okay? Now, if I want the conditional probability of B, where I know A has occurred, I took the intersection of the two and divided by what I'm conditioning on. So there, the probability of A. If I want the conditional probability of A, where I've now conditioned on B occurring, that's still the intersection of those two events. It's just I'm now dividing by, well, I'm conditioning on something different. I'm conditioning on B, so I'm dividing by the probability of B because that's what I conditioned on. Okay? So once we have that, and actually, so we're working backwards. So say we start here. Now, if we rearrange this a little bit, we can also get, right, if I just multiply both sides by the probability of A here, now I can solve for the intersection taking the conditional probability and multiplying by what I'm conditioning on, right? So I think the visual kind of gave us this, or gave us a good idea or intuition behind why this holds. And from there, it's just to rearrange the equation a little bit, multiply both sides by the probability of A, so that we can solve for that intersection of the two events, being the conditional probability times what I'm conditioning on. And because it doesn't matter if we write this as the probability of A and B, and what actually might make a little more sense here, to connect it with something that we talked about earlier in the class. It doesn't matter which way I write this, right? These two things are the same. The probability of A and B is the same as the probability of B and A. So I can find the intersection of these two using either of these equations, right? So, you know, it helps me sometimes to be able to use this, you know, if I know the probability of A, if I know the probability of B, and you could kind of use this equation to find that intersection as well. Got usually a couple of different ways of finding the same thing. Okay. Any questions before we keep moving here? All right, so here's kind of a summary of our probability rules. So I kind of glossed over, we talked about this on Friday, but that complement rule, that addition rule, and then kind of our multiplication rule, right? So with those in mind, what if I wanted to find the conditional probability using a contingency table? Okay. Well, I know that I should be able to rewrite a conditional probability as the intersection of the two events and then divide by what I'm conditioning on. So if I use that, how can I find this conditional probability? So it'll be the intersection of these two events, which would be what? So if I want the probability of R1 and C2, what would that be from this contingency table? Yeah. So if I want R1 and C2, the intersection, that's what those top four cells represent, that's 0.2. But from there, I have to then divide by what I'm conditioning on. What am I conditioning on here? C2, right? So I'll take that 0.2 and divide it by the probability of C2, which is 0.5, 0.2 over 0.5, whoops, gives me that 0.4, okay? So I can, even though it's not like directly given to me in the contingency table, I can use this multiplication rule because I can always find the intersection of two events and the probability of an event itself from the contingency table. So I can use components in the contingency table to help me find these conditional probabilities, okay? Questions on that one? So we'll save this for next class, but we'll kind of pick back up here. I'll probably do a little bit of a review with these conditional probabilities, and then we'll talk about whether or not events are independent, okay? We'll then kind of work through that. I'm guessing, let's see how quickly. Yeah, only 4 or 5 slides, kind of start class off. And then I'll jump into Excel, show you how we build our own contingency table, and then we could use those values to find some pretty interesting things, I think. So that'll be up on Canvas under the in-class data folder. Make sure you get on and get that Learn Smart done by the end of class, or sorry, before class starts Friday. Just like I said, should be 5 or 6 minutes. The other 2 homework assignments, the Connect and Excel that were assigned last week, try to start working on it as much as you can early in the week so you can get questions to me and you can make sure all of you get as many points as possible on those, okay? All right, I'll see you guys on Wednesday.